Welcome to the Mining and Metallurgical Society of America webinar series. MMSA is an association of mineral resource professionals whose members represent all facets of the mining and metallurgical interests, both domestic and internationally. MMSA has always been a cohesive group of senior people from the mineral industry. The society is dedicated to increasing public awareness and understanding about mining and why mined materials are essential to modern society and human well-being. The society concerns itself with fundamental principles and with problems facing the industry in such areas as legislation, economics, and education, as well as environmental concerns, labor relations, and health and safety. Representatives of the society from time to time also testify before legislative bodies and provide advice to federal agencies. I'm Kristen Guerin-Davey, MMSA member and new social media and webinar director. I'll be introducing the webinar for today. The title of today's webinar is The First 200 Years of Aluminum, What Comes Next by Ken Evans. Questions can be entered in the chat. The speaker will answer the questions after the presentation is complete. I will hand it over to Alistair to introduce our speaker.
Thanks, Kristen. Our guest today is Ken Evans. Ken's joining us from the UK, so we definitely appreciate him staying up late tonight to give us this webinar. Ken is a chemist with a Bachelor of Science and a PhD from Manchester University, and he spent over 50 years in the bauxite, aluminum industries with Alcan and the various entities that today exist as Rio Tinto Alcan. Ken has comprehensive expertise that comes from holding a wide range of technical and management roles, both in research groups as well as in operations. Ken still works for Rio Tinto Alcan. He's also a consultant to the bauxite aluminum industries at large, and is a member of the International Aluminum Institute and quality manager for the EU-funded Reactive project, which is a €10.5 million project that looks to promote the use of bauxite residues in cement. Today, Ken will speak to us and provide an overview of the alumina and aluminum production, the current status of aluminum production, factors that drive the location of mining, smelting, and refining locations, the current state of production and recent changes to the industry, as well as the challenges and opportunities that the industries face moving forward, and much more also on the future of alumina and aluminum. All right, Ken.
Thank you very much indeed for the introduction. First of all, an apology. I may, of course, use the wrong terminology and say aluminium instead of aluminum, but I've tried very carefully in my slides to take out all my aluminiums and also use a Z instead of an S. But apart from that, shall we start? I was going to talk about the first 100 years, but then I thought, well, seeing as we're nearly at 200 years, it's probably worth going back to the beginning. But as I put all the slides together, I began to realize that it's really aluminum is a growth industry, enormous growth, but it's very much in crisis in many ways. So there are quite a few aspects of that I'd like to talk about. So the topics, bit on the early history, overview of the technology, driving forces behind why plants are where they are, some data on the current production of bauxite, alumina, and aluminum, how it's changed, and it has changed phenomenally in the last 20 years. Alistair's asked me to include a few things on smelter grade alumina and the non-metallurgical grade aluminas. And then we talk about the major issues facing the industry and a few attempts to say what's next. So we all know about alumina. It's the most abundant metal in the Earth's crust at 8.23%, and it's the third most abundant element in the Earth's crust. Doesn't exist in nature as a metal, which is part of all our problems in the industry, but it's the main component of many rocks, aluminosilicates and clays. And the other elements in that group are gallium, indium, and thallium. Little bit of early history. So aluminum compounds were known by the Egyptians, 1000 BC, and the Romans as alum. It was found in, you actually get chunks of potassium aluminium sulfate in places like Egypt, and they used it as a mordant for dyeing and for tanning. So people knew about it, but they spent ages trying to isolate it. Humphrey Davy is the one who first really tried to isolate it, and they did a lot of work with things like potassium vapor to break down the very strong bond between the aluminium and oxygen. A key next aspect of it was 1821, when the bauxite was first identified in the south of France. They were looking for iron ore deposits, and they came across this material called bauxite, which was actually a hydrated alumina. So it was a sort of a mixture between aluminum hydroxide and aluminum oxyhydroxide. Ørsted was then the next one who put a lot of effort into trying to isolate the metal. He did it by passing a stream of chlorine gas over alumina and carbon to make aluminum chloride, and then used a potassium amalgam to try to react with the alumina, reduce it, and extract it in that way. So impure aluminum amalgams were found, but no pure alumina. So 1827, and Wöhler prepared the first samples of what were regarded as pure aluminum. He again used potassium metal in his process, and he nearly succeeded, but then stopped on it, but then came back and then used slightly different approaches and actually made pure samples of aluminum at that time. The first significant production, though, was done by Henry Sinclair de Ville, who used sodium instead of potassium. This greatly cheapened the process. And at that stage, they started to make significant tonnages of, well, when I say significant, that tons of aluminum as opposed to a few grams. It became it was regarded with great significance, and Napoleon was actually used it at one of his banquets, and the lower orders used gold, whereas the people at the top table used aluminum cutlery. Napoleon supported it because he was hoping to develop aluminum body armor. Something closer to home for you, the Washington Memorial in 1884 was topped with some pyramid of aluminum. This had acted as a lightning conductor, and of course was a good resistance to weathering. But the real process, as we know it today, was developed by two people. And there's quite a story about the history of this, because they both were working at the same time. And in 1986, they both were able to isolate aluminum. They did it with a electrolysis method where they passed a current through aluminium oxide. And of course, the problem with aluminium oxide is the melting point is over 2000 degrees centigrade. So it was done with a molten cryolite bath. So they used aluminium fluoride mixed with the alumina to create the right conditions for doing it. A lot of controversy at the time of who did it first. and it really, really was very close. And it ended up, because of the different patent laws in Europe and North America, Hall got the patent rights for the United States, whereas Herut had it for Europe. Those are just the actual patents that were done. Quite a coincidence, but they were both born in the same year and both died in the same year. And there's been a lot of discussion about why they should both have come up with this quite revolutionary discovery at the same time. There's no evidence of any collusion between them, and it really is a case of people working in a particular field coming to the same conclusion at the same time. But it's quite an interesting history. The next major development, and if this hadn't happened, then the whole Herut process would not have been successful. A Russian chemist working in St. Petersburg was trying to make aluminium hydroxide, and he was able to, he added aluminium or aluminum hydroxide as seed and was able to produce high purity aluminum hydroxide in this process. This enabled a very high purity feedstock, which was ideal for using in the smelting process. So the first alumina plants go back to one in France in 1893, Gardanne, which incidentally only was operating until about 2 years ago. So it ran all that time. In the UK, at Larne, there was a plant that used local bauxite. And then in the States, Pittsburgh Reduction Company built a plant in East St. Louis. Production of aluminum itself, there in the United States, it was Hall got together with, I mean, he was well supported financially at this stage. And the first smelter was in Kensington, just outside Pittsburgh. And that started in 18th of September 1888. Produced about 20 to 25 kilograms of aluminum per day, but quickly accelerated to 240 kilos a day by 1890. In Europe, things were happening at exactly the same time. In Switzerland, Herut was backed by the Swiss Metallurgical Society, and they built a smelter at Neuhausen, in essence using hydroelectric power. And by 1895, it was producing 450 tons. This later became Alu Suisse. France, it started in 1889 near Grenoble, again using hydroelectric power. And in the UK, in Scotland at Foyers, again using hydroelectric power. The first research director of British Aluminium was actually Lord Kelvin, responsible for the Kelvin temperature scale. You might be interested to know at the time, in 1894, he was employed at a salary of £1,000 a year, which I should think was pretty generous in those days. Just a comment too about in France, Herut got the backing of the French Metallurgical Society. So it's very interesting you've got metallurgical societies playing such a key role in the developments of these metals. So you all probably know about the quantities used because it's repeated so many times, but you need 4 tons of bauxite to make 2 tons of alumina, which then makes 1 ton of aluminum metal. The big downside is you also produce 2.5 tons of bauxite residue or red mud, and about 16 tons of carbon dioxide equivalent. So it'll vary obviously, and it's 4 tons for hydroelectric power, but 20 tons for coal. So you can see the main products of your process are not aluminum, but materials you don't really want. few comments on the types of bauxite. Of course, bauxite is found very widely across the world. You've got the lateritic ones, which are high in gibbsite, are not found in equatorial regions like Brazil, Ghana, and Guinea, and then the karstitic ones, which are high in bermite, normally found in the more temperate zones. The alumina formula for those is I've shown as bermite, gibbsite, and diaspore, and the main impurities are iron, typically 35 or so percent, and then titanium, calcium, silicon. Silicon is crucial, or can be a really negative material in the bauxite. If it's reactive, then it'll react with the aluminium compounds and then reduces the efficiency of the process, or it can be crystalline like quartz. When bauxite is purchased, it's the two criteria they use are the alumina content and then the reactive silicon. Minor impurities, some of these are like chromium, highly problematic in some applications, and rare earths, and there is a number of radioactive species there, which can cause a problem in some bauxites, particularly, for example, Venezuela and Western Australia, but to a lesser extent in Jamaica. So the Bayer process, it's a very hopefully you can see my pointer. With the bauxite comes in, it's milled with steel balls, and it's wet milled with caustic soda. It then goes to a digestion system, which I'll talk about a little later. Then diluted. This is a process where the silica products can be extracted. The aluminum compounds dissolve as sodium aluminate. They are then washed, and you get a residue out of that called bauxite residue or red mud. The liquor, which is concentrated sodium aluminate, is then filtered, heat is recovered, and then seed is added. It's just like the traditional experiments anyone would have done as a child, where you use seed of aluminum hydroxide, and then it accelerates the precipitation of the more aluminium hydroxide. It's a process that operates 24 hours a day, 365 days a year, and you really can't stop it at all. It's if you allow the tanks to cool, then all the aluminum hydroxide will precipitate out, and it becomes a problem that you have to dig the whole thing out. So after filtration, the solid aluminum hydroxide is recovered, and then it's calcined. The traditional way of doing it was rotary calciners at about 1200 centigrade, but now it tends to be fluid flash calciners. The digestion conditions are dictated by your type of bauxite, but typically for the hydroxide ones, they're 140 to 150 at 3 atmospheres with very concentrated sodium hydroxide. Bermite, which is the, should we say, the monohydrate, higher temperatures, higher pressures, and higher concentrations of sodium hydroxide. Diasporic bauxites, which are used a lot in places like Hungary and Greece, even higher temperatures. So the main industrial process, which was developed by Bayer, is still used today. About 96% of the alumina produced globally comes from the Bayer process from bauxite. About 2% comes from nepheline cyanide, and that tends to be in Russia, Siberia, where it's a very different process, and you get cement as a byproduct. There's also a modest amount of Bayer sinter root production. This used to take place in the United States in the plants in Bauxite, Arkansas. It's a very high silica bauxite, so they have to do a calcination stage with the residue at the end of the process, where they use calcium carbonate and sodium carbonate in the process. The initial plants were, 10, 20,000 tons. Now, many of the plants are 3 to 4 million tons a year, with the largest at 6.3 million tons. On the left, you have the design from Bayer, which goes back to 1893 at 10,000 tons. The plant on the right is the one in Brazil, Alunorte, with the Amazon there in the background. Rationale behind the plant location, certainly for alumina, power was historically crucial, very often coal, often lignite, particularly in places like Germany, where there's a lot of low quality brown coal. Availability of bauxite is a requirement. A port, and then historically they tended to be in industrialized areas. This then changed, and by the 50s and 70s there was a move to places like Jamaica, Suriname, Australia. The plants then were much larger. They were typically over 2 million tons a year. The previous ones being more like 650 to 750,000 tons a year. Big changes in the 2000s, very political, huge increase in production in China and India, which I'll come back to. And the future, we'll talk about that later, but political, bauxite availability, bauxite residue issues and possible taxes, China, India, and Indonesia are all going to be a significant part in that. The rationale for the smelters, power, you might say power. Hydroelectric power, all the early ones, as you note, were where there was hydroelectric power, and that's becoming growingly important. They tended to be in industrial areas. The waste from them is much less, so you can have it in a town, shall we say. There was a trend in the 1970s to more integrated plants where they did everything. They made the alumina plus the metal plus casting and even things like rolling. So the operations were much bigger. 2000 saw big moves to the Middle East because of cheap gas and big changes with growth in China and India. Future, green electricity will be crucial. Political reasons for moving things, political stability in the country you're going to be in is crucial. And then possible carbon taxes that will influence the type of fuel you've got. Just a few comments on changes in the alumina production process. In essence, chemically, it is identical to that which Bayer designed in the 1890s. Huge scale up, as I said, which gives process efficiencies. The extraction conditions have changed so that you sometimes add better quality bauxites if your yield is poor. Sodium or sodium hydroxide is the main raw material used as besides the bauxite. So control of that is very important and improves all the time. Better heat recovery as people are concerned about energy costs. Growing importance of water utilization, with some plants having to be zero discharge. Better control of crystallization, such as particle size and morphology, and better management of the red mud. There are a few alternatives to the Bayer process that have been tried. Some use anorthosite, where it's mixed with limestone and sodium carbonate, and then the mixture's calcined at just over 1250, and then you leach the aluminate liquor out of that. Nepheline, as I said before, tends to be done in Siberia. Clay, a lot of work going into acidic routes to extract the alumina component of clays, which typically have about 27% alumina. Fly ash, waste from coal, has got, again, about 25% alumina. And there's been a number of small plants that have started in that, but it doesn't seem to be growing very strongly. And a lot of interest in a process called the Peterson process, which used bauxite, limestone, and coke, which you calcined. You recovered the pig iron, and then you were left with a calcium aluminate slag, which you leached. Plant, 17,000 ton a year plant, ran in Norway between 1928 and 1969. Keep having attempts to try to resurrect the process because of the avoidance of red mud. Very quickly, the electrolytic cell. You have a carbon tank, which you then fill up with cryolite, and you slowly add aluminum oxide to it. That dissolves in it. The aim is to get the temperature down to less than 1,000 centigrade. So you use things like aluminium fluoride, lithium fluoride, magnesium fluoride, and other products to reduce the temperature. You pass a current between it, very high currents at about 5 volts, and these are two carbon anodes. You then get a reduction of the alumina. The molten aluminum floats on the bottom, and you can either suck that off or you can drain it off at periodic intervals. And the carbon anodes, of course, slowly disintegrate. They last about 2 weeks, and then you replace them. But it's the reaction between the carbon and the oxygen that does your reduction. I'll skip that, but if anyone wants more detail of the electrolytic process, we can come back. Changes in the process. The initial anodes used were called Soderbergs, and they were self-baking. So you put pitch in, and during the reaction they baked, but there were concerns about polyaromatic hydrocarbons coming off. But you'd be surprised that it was only in the 1970s, 1980s, they started to be removed. There are still some going in some parts of the world, but they then brought in these pre-baked anode ones. They've gone to higher currents. The average power intensity is falling. Currently, it's typically about 15 kilowatt hours per kilogram of aluminium, with the best being less than 13. Big goal has been the non-consumable anode, which we'll talk about later. In fact, today, Rio Tinto announced the new carbon-free alumina smelting cell, which is going to be set up in Arvida, up in Canada, where they expect the first production by 2027. The industry has been talking about this for many, many decades. I can tell you when I started work in 71, it's just around the corner. And of course, it's nearly there, but it's still 3 years away, and then on a very small scale. A few figures on production. This I found really quite concerning. It wasn't, I sort of knew it was happening, but when I started to put the figures down, I realized how significant it was. Look at China, the green blob, followed then by Russia, India, Canada, United Arab Emirates, which didn't exist 3 years ago, Bahrain, which didn't exist 6 or 7 years ago. So the changes have been phenomenal. This data just very quickly shows you data for 2000 in blue and 2023 in orange, just to say that many places have stayed pretty static, but look at the growth in China, India, and then places like the United Arab Emirates, which didn't exist, and sad to say, the USA declining. Number of primary aluminium smelters in the world, about 200 globally, 6 left in United States. Fortunately, you have Canada nearby that has 10. But when you look at China, you have 96. Russia has 10. India has 7. Europe has about 12. But you see huge movement of the industry to the Far East. This is some data. Between 2000 and 2023, the aluminum production rose globally by 103%, but the tonnage in the United States fell from about 3.7 million tons a year to 0.75. The increase in China over that period is phenomenal. From 2,600 to 41 million today. Huge growth in India, Middle East, and a steady decline in Europe, except for Norway, where it's hydroelectric power. Venezuela has stopped and Suriname has stopped. Little data on the United States, where you can see that the current primary production is 750, but you see the consumption is about over 4 million tons a year. So a big disparity between the consumption and production in the USA. Slightly different source, this data, but again, you can see how China has come from absolutely almost nothing in 1980 to quite low in 2000 to world leaders at the moment, whereas most others have either remained static or risen slowly. Alumina production, that's some data for different countries, but to give a sort of picture of that, there's been steady growth in alumina produced, and it's grown from 49 billion tons in 2000 to 140 last year, whilst the United States has fallen from 4.8 million tons a year of alumina to 0.8. You've had closures at Sherwin, Point Comfort, Burnside, and St. Croix, and there's only one alumina refinery remaining in the United States, which is Gramercy in Louisiana. Europe has seen a slow but steady decline. There are only 5 alumina refineries left. Lots of closures. Gardan, which had been running since 1893, closed a couple of years ago. Ica in Hungary Burnt Island in the UK, Bergheim and Schwandorf in Germany, and the plant in Till series, which is in Romania, is currently shut down. Closures in Australia, two big refineries. One is Gove, which was a Rio Tinto one, which in 20 years ago was considered the lowest cost alumina plant in the world. And Kwinana, one of the big Alcoa ones, has just announced its closure and will be closing within 2 or 3 months. Jamaica has seen progressive closures. The Kirkvine plant has closed. The Alpart one has been taken over. As it was taken over by the Chinese, and is now shut down. And in Suriname, the Sorelco plant owned by Alcoa is closed. And the growth areas, from just a few alumina refineries, China now has 44, with 20 having a capacity of more than 2 million tons a year, and they make 82 million tons last year. India, rapid growth there with now 10 alumina refineries. Saudi Arabia, there are 2 very recent ones making 4.1. Indonesia is going through, should we say, a revolution in terms of refineries, and it now has 4. Vietnam has 1, and Guinea, where most of the bauxite comes from, has 1, but there are several options being considered, and we'll talk later about Guinea. Demand for aluminum, however, is growing really very strongly. 2018, it was about 9,300,000 tons. Transportation being large, packaging large, and building and construction large. Growth by 2050 is forecast to be very, very strong. Up to 244,000 tons per annum, with a huge jump in transportation. One of the drivers for that is believed to be electrical vehicles. Whilst internal combustion engine uses about 70 kilograms of aluminum, and of course that's grown a lot in recent years, the electrical vehicle is expected to use up to 250 kilograms, used in the wheels, chassis, wheels, the battery pack, and electric housing protection. The forecast aluminum usage in electrical vehicles, which is now about 5.5 million tons, is expected to reach 12 million tons by 2030. Other big growth areas are seen to be solar energy and wind turbines. This shows the growth from 2013 up to 2050, and it by region. And again, China is the dominant force in this form. This is the regional growth between 2020 and 2050. You'll see that North America is modest and Europe is modest, whereas India, other Asia, Africa, and China are all showing much stronger growth, over 5%. This is forecast by the Indian Aluminium Association, and look how their alumina production has grown from 5 million tons a year in 2014 to 9 currently, with going up to over 20 by 2030. Alistair asked me to comment a little on different aluminas. Most of the alumina that's produced, about 95%, is smelter grade, so it's used for making aluminium metal. But there is a significant tonnage of non-metallurgical alumina, and it falls into three main categories: the commodity aluminium hydroxides, specialty, and aluminium oxides. The aluminium hydroxide uses are huge, the sort of thing that you would use every day and not really realize you're using it. But it goes into water treatment chemicals like aluminum sulfate, PAC, fire retardants, which is a very big market where it's added to many of the wire and cable products that you use every day in cars and buildings and homes, where it's replaced PVC. So, to say, many different uses. The specialty aluminum oxides, again, you find them in an iPhone, for example. Many old laptops have components with chips made out of alumina. It's used for armor plating for vehicles, flak jackets, tool tips, spark plugs, wear-resistant parts used in pumps in mines, even in bone replacement parts, hip joints and knee joints and artificial bones for the ear. Then you have the factory aluminas, polishing aluminas, tabular alumina. Prices are much, much higher, of course, than you might imagine for the smelter grade alumina. The issues, some big issues: waste management, very big issue for the industry, sometimes called red mud, going to be called processed bauxite in the future. We only decided that this week, but that's going to be the new name for it. About 170 million tons a year made. And the other waste, which is hazardous, is the spent hot linings from the smelter. 3% of global carbon dioxide emissions come from the aluminum industry. Concerns there about taxes for carbon dioxide emissions and the major need to decarbonize the industry, which is why Rio Tinto announced today that new carbon-free technology. Other big problem facing the industry is good quality bauxite. There is plenty of bauxite available, but the quality is declining, and that's a major issue. China has a lot of bauxite, but it tends to be poor quality because it's high in reactive silicas. And the big problem is the dependence on Guinea. So to touch on the bauxite residue issue, as I said, 170 million tons last year. The range that's produced per ton of alumina is dictated by the bauxite you use, and it can be anywhere between 0.5 and 4 tons of bauxite residue per ton of alumina. There are about 75 active alumina refineries and over 50 closed legacy sites, which will be very expensive to rehabilitate. It used to be disposed of in the sea. The Japanese did it. Ships were loaded, took it out into the Pacific. France and Greece disposed of it in the Mediterranean. In the UK, it used to go into the Bristol Channel. In the United States, it used to be dumped into the Mississippi and then swept out into the Gulf. And there's only 2 to 3% is used in any useful application. The world has about 4,000 million tons in stockpile, which is an enormous deposit to mine if someone finds a good use for it. That's bearing in mind the time. That gives you some idea of how the carbon dioxide is emitted from the process. But you see 71% comes from the electrolytic process. Casting is then a significant issue. Refining is a modest issue, but nowhere near as significant. That's some more detail on that, which gives all the emissions, which is anyone interested, we can come back to. This is the amount of energy required to produce aluminum by region. One thing that's certainly surprised me in recent years is just how China, which was extraordinarily bad, is now becoming much better. They are using more hydroelectric power, so their energy per unit weight is actually now much better than many other countries. Places like Europe have a mixture, where Norway is very good, Iceland is good, other parts are bad. In North America, you have hydro power in Canada, which is obviously beneficial for North America. I shall skip that. It's more detail on what they're doing in the smelting system to reduce power. I shall skip that too, because it's quite detailed on the emissions from different aspects of the process. But you can see the electrolytic process is by far the dominant contributor to everything from PFCs to carbon dioxide. That's bauxite residue generation. Just a couple of pictures of what happens if you don't store it properly. This was in 2010 in Hungary, and the dam wall burst. Those yellow things at the bottom, as you can see, are dump trucks and diggers, just to put the whole thing in scale. Pretty dramatic. 700,000 cubic meters of caustic slurry were released because of the dam failure. 10 people killed, 150 hospitalized, 3 villages overwhelmed, 300 houses destroyed, extensive contamination of the River Danube, and very, very negative publicity. And the media was full of comments about high radioactivity and arsenic and chromium releases, some of which, of course, were not true, but it's the damage is done because no one reads the corrections a few days later. Worth looking at the bauxite trade flows. This is data from last year. And the thing to look at is the blue circle in the middle, which is Guinea. And you can see they are supplying bauxite to everyone. 117 million tons a year flew out of Guinea to China, the Middle East, not to the Middle East, to Canada, and to Europe. Australia is the next biggest exporter, with about 37 million tons, mainly going to China, and that's mainly from the North Queensland area of the Weipa deposits. For United States, their bauxite comes in the main from Jamaica. Little bit on prices just to show how volatile it is. That is some data on, remember, about the bauxite makes up about a third of the cost of the alumina. So the bauxite changes are very dramatic in terms of the cost of alumina, and hence the cost of aluminium. Alumina trade flows, worth looking a little at that. Australia is the big exporter, 17 million tons a year of alumina, and some going to China, some going to India, a lot going to the Middle East. and some going to Canada. That's partly, of course, that some of the operations are owned in Australia by Rio Tinto, and it goes to their own smelters up in Canada. The big importers are Russia, Canada, so very strong growth has continued despite global problems. Significant decline in aluminium smelters, and America now only has 6 left, so its position is very much diminished. Very significant decline in alumina in the US, only 1 refinery left. Similar patterns in Europe, both West and Eastern Europe, with plants in Hungary and Romania and other areas closed. There's huge growth of both alumina and aluminum in China. India is investing very strongly. And one of the big new things is in Indonesia. Indonesia had or has a lot of bauxite, but the government is very keen to limit exports of bauxite and insists that you must buy the bauxite and use it within the country to make alumina itself. So that there's been a ban on exports unless you invested in the country. The other problem, as you saw, was the growing reliance on Guinea. It's got huge reserves, but it is politically very unstable. A number of plants have been designed there. In some cases, millions spent on designs, and then the government has changed, and the new government has, I can put it politely, asked for more bribes, and the plants have not been built. So the future demand is strong, driven very much by lightweight transport systems. Difficult to reverse loss of alumina production. Very difficult, as no new alumina refineries I would think of in the United States or Europe, unless there's political intervention. Even though you've got strong problems with things like the red mud or the bauxite residue, which will be unacceptable. Whereas the new refineries are in India, China, and Indonesia, possibly Guinea, but that's questionable. It's not quite as difficult to reopen a closed smelter, but it is difficult. Political intervention will help, but you do need power, a lot of power, plus alumina. And by the time you've closed your alumina operations, it's pushing up your costs. So new areas of smelters will be wherever there's hydroelectric power, solar power, sometimes underground heat storage, such as in Iceland, and nuclear. So locations: Canada, Iceland, Siberia, China, and the Middle East. Strong growth in Indonesia, and the decarbonization of the process. So just a final thought, since I've been talking, the alumina industry has produced 500 of these filled with bauxite residue, which shows what a big problem it is. So anyway, thank you very much indeed for your attention. Any questions?
Great, thank you so much, Ken. We do have one question in the chat so far, and if anyone else has any questions, feel free to type them in the chat. From Robert, is there any potential for shortfall in bauxite resources or reserves? Are we able to match the project growth and demand over the next 25 years?
Sorry, I missed the project. Sorry, the bauxite reserves where?
Globally.
Global, no problem at all. No problem. Somewhere I have a slide on that. Not sure I can find it quickly, but there is Yes. On the left, you have the global reserves, and those are in, as you see, about 30 billion tons of known reserves, very big in Guinea and Australia. And we're currently using 350 million tons a year. So you have a lot of, and those are proven reserves. And the moment they run out, you go to clay. We actually did a project on producing alumina from China clay waste, and it is a perfectly good alumina. You could use that. The only downside is one of the things I didn't mention is the Bayer process plant is made out of mild steel, and the plant that was built in 1893 still had tanks from their operating 3 years ago. So you don't get corrosion. Whereas some of these other routes that use low pH, strong hydrochloric acid means you need Hastelloy or some nickel alloy as the material construction. So it really, really pushes up the capital cost.
Gotcha. We have another question here from Elizabeth. The decline in alumina and aluminum processing in the USA and other places you mentioned, how much of this is due to increased environmental regulation and how much is due to other economic reasons?
Mainly economic reasons. What's happened, in fact, Europe has been much worse. We've seen a decline. I've seen it as very disappointing, is that the company that I work for, still do, Rio Tinto Alcan, invested very heavily in better smelter technology and ensuring no emissions from the smelter, only to find that the costs go up, so you end up closing the plant, and then it's made in China, where the environmental regulations are much worse, but there's no concern about it. The other big problem is the alumina plants are closing because of what to do with the bauxite residue. In the UK, the plant was closed because of a tax. They put a tax of $20 a ton on the alumina when you disposed of it, and that just killed the plant. So whilst regulations are tight in the US, it's not really been the bauxite deposits in Arkansas are poor. They are very high silica, so you can't use the conventional Bayer process. You have to use this extra calcination stage with limestone and sodium carbonate, which pushes your costs up. So
That's a great segue into a question from Alistair. How tied are alumina refineries to the specific bauxite they were designed for? Can refineries easily switch to a different feedstock or no?
Pretty much. Most will use 2 or 3 bauxites. They will use there are a few exceptions, like if you're using a diphosphoric bauxite, you need to have very high temperature digestion conditions, and only a few would have that. But most modern plants would be able to do a high temperature digestion, so they would balance a mixture of bermitic and gibbsitic bauxite. So yes, you can change. You wouldn't want to be changing very rapidly, but you can certainly play the tunes quite a lot. I just to say, of course, the Chinese have become adept at using bauxites from any source because they've had to, because their own bauxites are very poor quality. So they've been buying any mine that comes up for sale. They've been buying, and they've got round to using it.
Gotcha. Does anyone else have any questions for Ken today? Okay, I'm not seeing anything. So with that, many thanks to Ken Evans for his excellent presentation. Thank you so much to everyone for attending the webinar. We have a break in our webinar series lasting through to September. You'll get a notice of our upcoming webinars as details are finalized. The webinars are generally scheduled for the third Friday of each month. All of our webinars are also uploaded to YouTube and can be accessed through the mmsa.net website. The video of this webinar will be on the website within a week. The MMSA webinars are supported by the MMSA Jacqueline Foundation. We will send you a notice when the video and slides are posted on the MMSA website, and the webinar is now ended. Thank you, everyone.